This is the first lesson in our thermochemistry and rates unit, which is a unit covering 3 chapters in the textbook. Thermochemistry specifically is covered in chapter 6. Then there is a chapter on entropy, free energy, and equilibrium, which is chapter 18. And chemical kinetics connects with thermochemistry, which is found in chapter 13. Chapter 6 covers the study of thermochemistry, and when we're looking at thermochemistry, it's actually an area of thermodynamics. And physicists are responsible for studying thermodynamics overall, which is the study of energy and energy transfer. When we study thermochemistry, we're specifically studying the energy involved in chemical reactions. Before we begin really looking at different ways that we can study the energy involved in chemical reactions, we need to understand what a thermochemical equation is. Once we've done that, we're going to look at our first way of calculating delta H in this lesson. And delta H is called the enthalpy. At the end of this chapter, you're going to have 4 different ways that you can calculate delta H depending on what type of reaction you're studying and what kind of information you have available to you. So first of all, let's look at this thermochemical equation. 2H2 plus O2 going to 2H2O. You can see that there's an enthalpy provided here, a delta H value, and you've seen this before in our previous study of equilibrium. Okay, we used it to help us study Le Chatelier's principle. Okay, you'll recall that the sign on the delta H lets you know whether the reaction is exothermic or endothermic. So a thermochemical equation has always the energy associated with that reaction provided. The other feature that is really important for a thermochemical equation, if it's going to be complete, is the states of the reactants and products. The states matter if you think about the energy involved in the reaction. If you think about this one here, the H2O, if I was producing liquid instead, there'd be a different amount of energy involved, because to go from a liquid to a gas, that requires energy. And that would be a factor in the actual delta H for this reaction. The other really important thing about thermochemical equations is to recognize the connection between the delta H and the balanced chemical equation. This is the amount of energy, and in a lot of cases it's reported in kilojoules, that is released, in this case because it's negative, when exactly 2 moles of hydrogen reacts with 1 mole of oxygen and 2 moles of water is produced. So there's a stoichiometric connection between the delta H values and the balanced chemical equation, which we'll investigate with a couple of examples. You'll see that sometimes we use kilojoules and sometimes people would put kilojoules per mole. Okay, both are acceptable. What we need to remember is that no matter what we have here, it's per mole based on the balanced chemical equation. So the reaction that we saw the other day was the thermite reaction, and this was the reaction between aluminum and rust or iron oxide. And what we want to know is the amount of heat that was actually released when 225 grams of the iron oxide was used in the reaction. So we've got a specific gram amount or mass of the rust that was being used. And in the thermochemical equation here, we've got the number of kilojoules that are released per mole. And in this case, it's per 1 mole of iron 3 oxide. So what we need to do is figure out, if we've got 225 grams, how much energy is going to be released. To do that, we need to find the moles of the iron oxide that we actually used. The molar mass of iron oxide is 159.7 grams per mole. Okay, so to find the moles of iron oxide, it's going to be 225 grams divided by 159.7. So we're actually working with 1.41 moles of rust. So if we look at the relationship, it's essentially a 1-to-1 ratio. For every 1 mole of iron oxide, we release this amount of energy. So if we're releasing 1.41 moles, if we're using 1.41 moles, then the heat evolved, or the energy released, is going to be equal to 822.8 times 1.41, okay, which is equal to 1159.2 kilojoules. Now you'll notice here that I didn't use the sign. A sign is the sign, or the negative, is a convention, so it's used to show us that it's exothermic, and it's also showing us the relationship between the initial and final delta H. It's also appropriate to use words to express that heat was actually released. So by saying heat evolved is equal to 1159, that's showing you that it's an exothermic reaction. In this next one, we want to know the heat evolved in kilojoules per gram of zinc sulfide roasted in the industrial process. Okay, roasting is really just a special kind of heating, like you're roasting for extended periods of time, sort of slowly. That's what roasting is. So in this process, for every 2 moles of zinc sulfide that's roasted, we release 879 kilojoules of energy. So unlike the first one where it was a 1-to-1 ratio, okay, we actually have a 2-to-1 ratio. So what we can do first is figure out how many joules will be released for 1 mole. Okay, so this is the amount of energy that's released when 2 moles of zinc sulfide is reacted. So really, for 1 mole, it's 439.5, okay, kilojoules per 1 mole of zinc sulfide. Okay, and if we're dealing with 1 gram, then the number of moles of the zinc sulfide is 1 divided by its molar mass, which is 97.45, or 0.01026. So then the heat evolved is the 439 times the number of moles, and we get 4.51 kilojoules. You can check that your work makes sense here because one mole is 97. Okay, we've only got part of a mole, so it makes sense that it's only 4.51 kilojoules. The other thing that we'll do before we start to calculate delta H is just review some of the features of endothermic and exothermic reactions to make sure that they're clear, and also look at how we can draw enthalpy diagrams to represent both exo and endothermic reactions. So an endothermic reaction, as you know, is one that absorbs energy from the surroundings. So when a reaction needs energy in order to proceed, it will take energy from the surroundings, and what that's going to lead to is to a temperature decrease. So when you have a reaction and the temperature drops, okay, you know that it is an endothermic reaction. This will be good as summary for later, okay, about the bonds broken and bonds made, okay, and we're going to be discussing that a little bit later on. To review the thermochemical equations, if it's endothermic, energy is a reactant, or you can have the delta H value reported with a positive sign to show you that it's an endothermic reaction. Both of these are appropriate for reporting a thermochemical equation. Because the enthalpy that we report is a change in enthalpy, we can show an enthalpy diagram, which actually shows a visual of the change in the enthalpy of the system. So in this case, the enthalpy is positive, change is positive, so that means that the enthalpy has increased over the course of the reaction. So magnesium carbonate had a certain amount of enthalpy or internal energy, and after the reaction, we had a greater amount of internal energy or enthalpy. So this gives a good visual, and the difference between these two is the 117.3. Okay, so this is our H1, this is where we started, and this is where we finished. Okay, so this is how you draw an enthalpy diagram for an endothermic reaction. Exothermic reaction, energy is released into the surroundings. So this time we experience a temperature increase. During the process of the reaction, the energy is being released. The surroundings absorb it, and that's why the temperature of the surroundings increases. For the thermochemical equation, the energy in an exothermic reaction is a product. Okay, so you can see it in this case, or we can report it with its change in enthalpy, or delta H, as having a negative sign. Because the enthalpy change is negative, we know that during the course of the reaction, the enthalpy has decreased. So I'm starting with a certain amount of enthalpy. I end with a smaller amount of enthalpy, so the delta H here is negative. And I write the reactants up here and the products here.